Well, today we're having the opportunity to be guided through the world of chemistry, and our guide is Professor Ann Valentine. And she's going to talk to us a little bit about medical metals, and we'll find out shortly what that all means. Now, some interesting things about Professor Valentine is that she grew up in Pittsburgh, and she went to school at the University of Virginia and then MIT. And when she was in college, she was a competitive swimmer. Anybody out there a competitive swimmer or like to swim? All right, well, you've got some good company. And another interesting tidbit is that she actually was a floor or dorm resident for Professor Aaron Lavick. So you can see we're all kind of connected. All right. So, well, anyway, without further ado, let's welcome Professor Valentine to the podium.
Thank you, Anissa. Good morning, everyone.
Good morning.
Well, welcome to my talk this morning, which is, as advertised, about medical metals. This is me, Ann Valentine. Here's my email if you find after today that you have questions and you want to ask questions. I encourage you, though, to interrupt me with questions if, while I'm talking, something occurs to you or you want more explanation. Please, by all means, speak up. It's fortuitous that I'm speaking this morning because it turns out this week, in case you didn't know, is National Chemistry Week. You have to search the Hallmark section pretty hard to find the cards, but in fact it is National Chemistry Week, October 22nd to the 28th, so maybe some of you guys in your schools will have some special programming. I celebrated National Chemistry Week by getting the official National Chemistry Week tattoo. There you go, can you see? So that all of you can similarly celebrate, we have lots of National Chemistry Week tattoos, and as you leave, some students will be giving you some lovely door prizes, which include proper tattoos, so you can celebrate in grand style this week. So this is our American Chemical Society mascot, the mole. On the tattoos, it explains why, but you see we have a little mole as our inspiration for the day, so he can just sit right there. So I want to get something out of the way at the very, very beginning by talking about what a chemist is and what they do. And so I want to see what you all think about this definition of a chemist. So what do you think about that one? Here's the sort of stereotype of a chemist. He's an old guy, and he's got white hair, and he's googly-eyed and crazy, you know? So what do you think? Is this a good definition? No, not a good definition. I mean, sometimes it's true. Some of my best friends fit under this description, but it's not always true. And so I'd like to start again about what a chemist is and what a chemist does. Chemists study the molecular nature of matter and how it interacts with other matter and how it changes. So we're really deeply obsessed with atoms and molecules that make up stuff and how the stuff changes and what it can make. So, for example, it could be that your dad is a chemist when he makes you a grilled cheese sandwich. If you are really hungry and the sandwich isn't cooking fast enough, what do? You turn it up, right? Turn up the heat. And it makes it cook faster. Well, why does that work? Maybe you don't think about it every time, but in fact, you're doing chemistry on the grilled cheese sandwich. Maybe your sister's a chemist when she puts these crazy teeth whitening strips on, right? What are those things anyway? How do those things work? I'm not talking about white strips today. Maybe you're a chemist when you get one of those glow sticks at a fair or a concert, right? And you all know if you go home and you want it to glow again the next day, you stick it in your freezer, right? And that makes it last more. Well, why does that happen? That's sort of strange. So even though you may not think about it every time, you're in fact surrounded by chemistry, and chemical principles impact you all the time. We also have some glow sticks for you at the end. So you can practice this part yourself. They're blue and white, Yale colors. Yeah. So the particular kind of chemistry that I work on with my students is bioinorganic chemistry. It's about metals in biology. And at the beginning, that might sound a little bit weird, and I want to spend a minute talking about bioinorganic chemistry. So it turns out that by about 1800, there was a division in chemistry between the chemistry of the molecules of life, which was called organic chemistry. Now organic means you pay more for it in the grocery store, but originally it meant it was carbon-based and a molecule that made up a biological organism. And at the very beginning, that was thought to be different in some profound way, by some mystical, process, that was thought to be different from the molecules of, say, minerals or stones or ores, and that was inorganic chemistry. And the funny thing is, we've known for almost 200 years that this is a false division. So this gentleman, Wöhler, is credited with sort of completely putting to rest the idea that inorganic chemistry and organic chemistry are separate things. So the experiment that he did was he converted ammonium cyanate, which was known to be inorganic, and he converted it to urea. So I want to show you those molecules. I have them in a couple different forms because I just want to remind you the way that chemists represent molecules. Okay, so here's ammonium, right? It's NH4, and there it is up. I don't have enough hands. There it is up there. So this is NH4. Here's cyanate. Now, some sicko stole all the nitrogens from our chemistry molecular model kit this week. Can't find them anywhere. So I had to sort of make homemade ones. So all through my today's lecture, the blue taped molecule or atoms are nitrogen. That's right. There was only one left. They teased me, right? They left just one. That's almost worse than none. Now they don't match. Okay, so here's ammonium, here's cyanate, right? This is OCN. And what Wöhler did was he heated that, and he converted it to urea, which is this molecule, which has the same atoms. Make a urea bracelet, right? Okay, and so it has all the same atoms as the other molecule, but in a different binding orientation. And urea was a product that was known to be organic. Wöhler knew this because it was isolated from urine. So it was organic. It was a biological process. And this, in 1828, really showed that there's no difference between the molecules, the atoms of organic and inorganic chemistry. But we still maintain this division, and we sort of joke about it. So there's sort of a healthy rivalry, really, between the organic chemists and the inorganic chemists. Now, another reason I showed this slide is to remind you of another, sorry, I put my urea down. To remind you of another way that we represent molecules, which is like this. So this representation is equivalent to this one. To save space, sometimes we just write the atoms, NH4. And chemists also write arrows like this to show that some reaction happens. So Wöhler's reaction was ammonium and cyanate reacted to make urea over there. Okay? So that we'll see a couple times again. This sort of way of representing, another way of representing molecules. Okay, so with that out of the way then, now I've assured you that there's nothing weird about inorganic elements being in biology because they're all just elements. The particular thing that people like me study is the involvement of elements other than carbon in biological processes. And here are 3 examples that might come under this heading. So first of all, some biological molecules naturally contain metals. My example here is hemoglobin. Right now in each of your blood, hemoglobin contains iron and it's transporting oxygen to your tissues. And so we need this for life. A second example to admit the downside is that some metals are poisonous. And so, for example, lead is poisonous to humans. And lastly, some metals are used in medicines to combat illness and disease. If you take pink Pepto-Bismol, the active compound in that is a bismuth compound. And so that is one example of a medical metal. We'll get to another one later. Today I'd like to talk about the first and third of these things. One reason is because I'm generally optimistic. I don't want to talk about metal poisoning. Another reason is because I want to do demos. Doing demos of metal poisoning might be not such a good idea to convince you guys to go into science. Okay, now it turns out that lots of metals are important in biology, and this is a periodic table. Now, as a chemist, I'm contractually obligated to show a periodic table within the first 6 slides. It's necessary. I really like this one because it only shows part of the periodic table, and it cuts off the part with carbon. So that makes the organic chemist mad. It's up here someplace, I don't know. So anyway, this shows the metals that are important in biology, and particularly it shows the ones that are naturally involved in biological processes in red. It shows ones that are involved in some kind of drug or probe molecule in gray. Okay, so we have a lot to choose from for our talk today. Lots of metals are important in biology. But before I talk about specific cases, I want to get one last thing out of the way, which is to be very clear about what it is that I'm talking about. So if you guys imagine a metal, you probably imagine something like my car keys, right? So they're hard, they conduct electricity sometimes. This kind of metal is not what I'm talking about today. If we imagined, let's start with iron. If we imagined solid iron, a hunk of iron metal, that's not the kind of metal that's usually involved in biological processes. Instead, what I want you to imagine is imagine just taking one atom out of that hunk of iron metal. Okay, so here it is. This iron atom has got 26 protons. That's what makes it iron. It's got maybe 30 neutrons. And the atom, if it's neutral, has 26 electrons. And you guys know the atomic structure says the protons and neutrons are in the nucleus. The electrons are around the outside, right? Okay, so everybody's color-coded here. Now, if I could ask you now to further imagine taking 3 of those electrons away. So here we have what we call an iron ion. So the ion still has the 26 protons. It's still iron. It's still got the same number of neutrons, but now it's lost 3 electrons. And so it's got an overall +3 charge. Okay, so now we're closer to what biology uses. Last thing I want you to imagine is I want you to imagine binding stuff to that iron. And we call that stuff ligands. So often, metals bind 6 things, ligands like this, and when they do that, they make an iron 3+ complex. So my point is that generally, in biology, we're not talking about hunks of metal being involved in some process. We're talking about metal complexes, so maybe just one or just a few metal ions bound to other stuff. Okay? So that's a little bit different than what you might imagine about metals. Okay, now, with that introduction then, I would like to tell you 2 stories today. One of them is about the first of those 3 involvements of metals I showed you before, about how a metal is involved in a natural biological process that protects you. And the second one is going to be a story about a medical metal, as promised, the story of the most successful metal-based anti-cancer medicine. So, my first one is about a metal in an enzyme. So, a few definitions. First of all, an enzyme is a catalyst made by biology. A catalyst is something that makes a reaction that's already favorable. That's key. A catalyst can't make something happen that's not going to happen, that doesn't have a favorable reaction on its own. But if something's favorable, a catalyst can make it faster. And the second part of the key is that the catalyst can't be changed by the event. The catalyst remains unchanged and can go on and catalyze the reaction over again. So my analogy here is that if you introduce 2 people to each other, and then they become friends, they clearly had something in common, right? You didn't make them be friends. They both liked soccer or whatever. They had something in common. They were going to be friends, but they might never have met each other. And so if you introduce them, then you're a catalyst for their relationship. And it doesn't change you any. You can go out then and introduce other people and have them be friends also. So in biology, we have molecules that do that same function, which, as we'll see, is a darn good thing for us. And I also want to admit, somewhat grudgingly, that I don't want you to go home thinking that every enzyme has a metal in it, because they don't all. My favorite ones do, but they don't all. So the one we'll see today does have a metal in it. So the particular enzyme we're going to talk about today is one called Catalase. It's got an easy name to remember, right? It catalyzes stuff. Its name is Catalase. That's good. And it really addresses the fact that as all of you breathe oxygen, now remember we said your oxygen's carried to your cells by the hemoglobin, so there's one iron involved there. Inside your cells, you respire that oxygen, and the intended product of respiration is water. So you're inhaling oxygen, you're making water. And that happens most of the time, but not all of the time. And so the bad thing that happens about 20% of the time is that the oxygen doesn't get all the way converted to water. it stops part way. And so inside your cells, you make a little bit of hydrogen peroxide. Now, many of you may have seen hydrogen peroxide in the grocery store. It's in the first aid aisle in little brown bottles. And the reason that you buy it in the grocery store is because you use it to disinfect things. So if you get a cut, maybe you guys have done this, right? You put a little hydrogen peroxide on the cut, and what happens? It burns, it does burn. It kind of fizzes, right? You get a little fizziness on your cut. Okay, what you're watching there is the hydrogen peroxide damaging any bacteria that might have gotten in your cut. You're probably damaging your skin a little bit too, but you have a nice protection. Your skin gives you good protection to everything below. So the reason that we buy this in the grocery store is to kill cells. And you could imagine it's really bad for it to get made inside your cells, right? It can go and damage the molecules in your cells. And so the good thing is that we have an enzyme, Catalase enzyme, that speeds up the destruction of hydrogen peroxide. Okay, so here's what happens. Here we have 2 molecules of hydrogen peroxide. I again have some here just to show you, right? So here we have the 2 molecules of hydrogen peroxide, right? And these convert to oxygen and water. So 1 molecule of oxygen, here it is. I had lots of oxygens, just the nitrogens were stolen. And 2 molecules of water, and those are shown up there. Okay, now remember I told you that one of the important things to remember about a catalyst is it can't make something happen that's not going to happen anyway. And the conversion of hydrogen peroxide to oxygen and water is really favorable, and it'll happen by itself. So you might wonder, why bother with a catalyst then? But the reason why is because without catalase, it takes a really long time for it all to go away. And so if you made some hydrogen peroxide inside your cell, it would take about a year for half of it to go away. And that's a pretty long time because you're making it all the time. You don't want those hydrogen peroxide molecules staying around. But if you have catalase, then it goes away, half of it goes away in about a minute. Okay. So we're going to watch this guy in action today. So first of all, I would like to make sure you notice how safe I'm being, right? We're going to be got gloves on. See, they even make cool purple ones now, so you don't have to look quite as dorky as your parents might remember looking in lab. Got semi-cool safety glasses, right? Okay, so here I have some hydrogen peroxide. Now, this is more concentrated, about 10 times more concentrated than what's sold in the grocery store. Because I'm a professional, so this is a better demo with more hydrogen peroxide. And so far, this demo is really, really boring because it kind of looks like water, right? So that's pretty boring. But in fact, what you've seen poured out here is 30% hydrogen peroxide. I'll move to the middle, sort of. So this is 30% hydrogen peroxide. It pretty much looks like water. And if we had a year to wait, we could wait for half of it to go away. But I figure probably some of you have other stuff to do, and they need this classroom for Monday. So we need to make it go away faster. Okay. Now, what we're going to use is this enzyme catalase. And I wanted to show you the molecule, the core of the molecule that catalase uses to do this reaction. Now, didn't think about the lab coat microphone issue. All right, there we go. Okay, so catalase uses a core of its molecule looks a lot like hemoglobin. So on the left, I'm showing you the hemoglobin molecule that brought the oxygen to the cell, at least the core part of it, the part that binds oxygen. Oh, surprise. Sorry. Over here on the right, I'm showing the part of catalase that does the chemistry. So they look a lot like each other, don't they? And part of what fascinates a chemist is, how come this molecule binds oxygen, but this one does something different if they look so similar? This is the kind of thing that keeps us off the streets. Okay, so we're going to see catalase at work. I'm going to put some catalase in that graduated cylinder, and we're going to convert the hydrogen peroxide in just a second. Now, it turns out that a lot of the catalase in your body is in the liver, believe it or not. And so what we're going to do today is use the catalase in liver, specifically chicken liver, to convert that hydrogen peroxide. So I went to the grocery store this morning, actually 3 grocery stores, and got some chicken liver. You would not believe the looks you get when you go into the grocery store to buy coffee, a muffin, and chicken liver at 8 o'clock in the morning. Hang on a second. All right, I should have opened this before it's not my usual brand. No, it's true. I had to go to a different store.
Would any liver work?
Any liver would work. That's a good question. So, what the heck? I thought I opened this well enough. Any liver would work because any organism that breathes oxygen, I'm okay. Oh, sorry. Any organism that breathes oxygen has this problem with not completely converting its oxygen to hydrogen peroxide. So beef liver would work, all that stuff. Okay, so I'm going to put the chicken liver in here, and the question is, what are we going to see? Okay, so here's what we're going to see. So the hydrogen peroxide looks pretty much like water, right? So seeing that convert to water, there's nothing to see. But the oxygen that gets made is going to make bubbles. And so the main thing that you're going to see is the oxygen making bubbles, and it kind of is going to foam up, much like the hydrogen peroxide that you put on your skin when you're cut. Okay? If you were up here, you might feel the hydrogen peroxide getting a little bit warm, because heat is another product of the reaction. Okay, so here we have the chicken livers. Right? Yeah. Okay, so here we go. Hydrogen peroxide, chicken liver. Ready? And there it goes. See? Yeah, pretty cool, right? Okay, so, hang on. Okay, so let's talk about what's going to happen then. So, yeah, sometimes I get a little crazy and it foams over the top, so we'll see how crazy I got. So what's happening is, right, these bubbles are coming from the oxygen that's getting made from the catalase, and the catalase itself is just turning over, and it's able to turn over multiple times. And so by the time, what it'll do is it'll consume all the hydrogen peroxide that's in here, and then it'll be ready for more. So I could, at the end of this, pour more peroxide in, and the reaction should start up again. Okay? So what you're seeing then is the action of this iron catalyst. Yeah, it's pretty gross. Okay. Yeah, you could. So this is mainly pure oxygen coming out the top, although it's not on such a big scale.
So the catalase is not consumed by the chemical reaction?
That's right. The catalase is a real catalyst, and so it can just keep turning over and over. If you cooked it, it wouldn't work as well, because the protein that's around it would all unfold, and it wouldn't really work so well. But as long as you don't cook it, you can do that. So we'll let that just bubble. It can be a semi-disgusting distraction for you guys while I'm talking. You have different ways of making it. So when I'm not a very good biologist, but when a white blood cell engulfs something, I think it can produce some hydrogen peroxide, like on the spot. But it's not the same hydrogen peroxide that gets made this way. Yes? It's not going to be a big difference, because even this hydrogen peroxide is still only 30%. So it's still 70% water. And it's true, some of the hydrogen peroxide would convert to water, but I've never seen a noticeable volume change. You can't buy more concentrated hydrogen peroxide than this. It's a little dangerous. It's a little explosive. Okay, so, and actually I wanted to say before I go on to something else that hydrogen peroxide is the thing in those white strips, right? So remember earlier in my intro of chemistry in your everyday life, I mentioned the white strips you put on your teeth to whiten them, and it is peroxide that's on those strips. So that's why they have this is why they have a shelf life. So when you go and if you find some expired white strips in your cabinet and you wonder, is it safe to use them? It's safe, but they're not going to do anything, because the hydrogen peroxide is decomposing, because it has the tendency to do that all by itself. And even more so if you put it on your chicken liver. But can't imagine why that would ever come up. Okay, so anyone else have questions about catalase before we do something a little different? Yes, in the back. Yeah, catalase is iron. So here's the iron right in the middle. That's the yellow, yep. Anybody else? Yes, question in the back.
If you put a different type, like if you didn't put liver in there, like let's say you put like ovaries or something in there, would it be the same?
Yes, but not as well. So there's less, there's a little bit of catalase in lots of kinds of tissue, but there's the most in liver. And so, yeah, you can use hamburger, other stuff, but this is the highest concentration, so it gives you the best foaming. Yes? Well, there are some small differences in the heme, but mainly it's the protein around it is different. I know, yeah. So there are some small differences. So like, just to pick one out, right, this is different from that. The protein around them is all different, but you're right, they look a lot the same. And how such similar molecules could do different chemistry is a totally profound question that we all think about. Okay, anybody else on catalase? Okay, so then in that case, my summary of part one, the enzyme catalase in the liver, which has an iron atom at its core, protects you from the leaked hydrogen peroxide that you make during respiration by making it convert faster to oxygen and water.
And by respiration, you mean in the cells, not our...
Right, in the cells, right. The molecular respiration, yes.
What would happen if we didn't have catalase in our liver or body?
The hydrogen peroxide it attacks other kinds of molecules, so it attacks DNA, for example. It makes breaks in DNA. That would be one bad thing that would happen. So it's reactive. I mean, you see the fizzing, and so it might make a mutation in DNA. Yeah, just non-specific bad stuff. Yes? It makes free radicals. Yeah, hydrogen peroxide itself is not a free radical. A free radical has unpaired electrons. But it makes OH dot, which has unpaired electrons and is a free radical. So it's kind of on the way there, although it isn't itself one. Okay, part two. Part two is the story about the medical metal. So for those of you who were here 2 weeks ago, you've actually seen a little bit of intro to this, but I wanted to start today's talk with another demonstration. So here we have, in the front you may have noticed my green beakers, and those beakers contain nickel sulfate. So, fresh gloves. So nickel sulfate is a metal salt, and I brought some that's solid just so you can see. So right? Okay, so there's solid nickel sulfate. It's beautiful green crystals. This is why it's good to be an inorganic chemist. Organic chemistry, they don't have pretty colors, usually. So, can you tell I'm a little bit, okay, a little biased, yeah. That's okay, though. Okay, so here's nickel sulfate crystals. Here's a nickel sulfate solution that I made, right? It's the same pretty green color. And then over there are 6 nickel sulfate solutions that are a little more dilute, right? So we can see the color changes. Okay, so what's already happened then in my dilution is that I took nickel sulfate solid, the solid green, and I dissolved it in water. And it made this beaker here, which is those beakers there, which is the pretty nice green color, right? So the molecule that's made inside that beaker is the one that I'm showing you here. So here is a nickel 2+ ion. So remember, a single atom of nickel has lost 2 of its electrons to make an ion. And it's got waters attached to it. So there it is. It looks kind of like this. And that's what's floating around in those green beakers. Another way to draw the thing is like this. Sorry, get rid of the disgusting stuff. So you can see. So another way to draw this is this way. So these are equivalent ways that a chemist might represent the molecule. And this is another one. So nickel with 6 waters, overall 2+ charge. And it's bonded kind of like this. Okay, that's what's in the beaker. Now you might wonder why that thing has color, right? So the reason that it has color is because, I'm reminding you, so in nickel 2+, there are 28 protons, a little different than iron, 30 neutrons, and 26 electrons. It's 2+. And these electrons are the important part. These electrons are why transition metal complexes have color and most organic molecules don't. Because what happens is those outer electrons absorb light energy, and they get excited to a higher energy level, and when they absorb light, you see a different color than white light. So in this case, the nickel is absorbing the red from the room light, and it's making it look green to you, so you're seeing what's left over, right? And so every time the light's hitting that thing, the electrons in the nickel get excited to a higher energy level, and they take the red right out of the light. And so you see the other stuff. Okay? So that's why you're seeing green, because the outer electrons, these outside electrons out of this group, are absorbing light and getting excited to a higher energy level. Right? Okay, so now let's do some chemistry with it. So what happens if we take this complex, this nickel with 6 waters, and we add some ammonia to it? Okay, so this is just household ammonia like you might use to clean the floor. So let's start with this. Okay, now I'm going to leave this beaker the same, right? This one's always going to be the same hexaquo here on the end, so you can see that one. And we'll add stuff to the others. Okay, so often people like the stir plate better than anything else I do. We use these things in lab so the students don't have to stir all the time, right? It's got a little magnet at the bottom, and it's stirring around to mix the solution. Okay, so first I'm going to add to the first one some ammonia. Okay, assuming I can get the thing open. It's a different one. Okay. Okay, so here we go. Ready? This is also good. This is a pipetter, so automated, so you don't have to use a bulb or anything like that. Okay, ready? Here we go. Actually, let me use a little bit more. Making sure it's all the way blue. Okay. So that was neat, right? That one turned blue. Okay. So what you just saw then, was that, right? Ish. I mean, it's not quite the same color, but close. And what you're making there is this molecule. This one has all of those waters that used to be bound to the nickel exchanged for ammonia, NH3 molecules, right? So this is the thing that's in that beaker now. And again, we could write it some other different ways to save some space, right? That would work too. So this thing with different ligands bound to it has a different color than the one with the water bound to it. So that's weird. How does that work? Well, here are the two things I've made so far. And the reason that they're different is because they have different ligands bound to them. So you could imagine, right, if I'm the nickel hexaquo complex, right, and I need to get up an energy level, right, okay, here I am. I'm at an excited energy level now. Jumping on furniture was bad for Tom Cruise's career. We'll see what it does for mine. Okay, so here I am, right? I'm the nickel hexaquo. I've even got a shirt that matches today. Right? So I'm the green one, right? It took a certain amount of energy for me to do that, right? To get up here to this higher energy level. If I were a different complex, if I were one of you smaller type people, you could imagine it might take you a different amount of energy to get up here on the table with me. So it's not weight exactly. The weight is an analogy that I'm using. But a different complex with different ligands bound to it takes a different amount of energy to get excited to a higher level, right? And that means the light gets absorbed at a different color. So, so the energy of the light that's absorbed by those outer electrons is really sensitive to what's bound to the metal. And that's why these nickel complexes have different color. So the one is absorbing to make it green. With different ligands, the absorption makes it blue. But it's all the same metal. And that's another thing that inorganic chemists think is really cool. Okay, so, okay. enough jumping on furniture. So here again are your two things that we've made so far. Okay, let's bind something else. We'll bind something else to the metal. Okay, so the next thing I want to bind to the metal is something called ethylene diamine. Sorry about my cooler. So ethylene diamine is down here. This is the next ligand that I want to use. So one reason I've drawn it like this is to again show you the tyranny, the horrible, horrible tyranny of the organic chemists. When we don't show an atom, it's assumed to be carbon. How rude is that? They just assume it's carbon. So here, this molecule has nitrogen, carbon at this corner, carbon, assumed, nitrogen. And this particular molecule is called ethylene diamine. So the next thing we're going to do is add some ethylene diamine. Okay, so what I'm going to do here is add just a little bit of ethylene diamine to the first beaker. Okay, so here we go. Okay, ready? Okay, blue again, but kind of a different blue, wouldn't you say? Looks a little bit different than the first one. Yeah, that one made a solid. I don't know if you guys can see, but that one kind of made a solid on the left-hand side. This one is still pretty clear, so it's a little bit different. Where's my, oh, there it is. Okay. So the complex that we made, the color looks something like that. The complex that we made is this one. So now we took what used to be 6 waters, and we replaced 2 of them with those 2 nitrogens. Okay, and so writing the atoms on, it looks kind of like that. And we might make the cartoon like this. So here's the nickel with this molecule bound to it, and the other 4 waters. Okay? So now there's the 3 that we've made. So now let's make something different. Okay. Next, I'm going to add more of the same thing. Okay? So here we go. And it turns sort of a darker purple, right? So that complex with the darker color is this one. So now we put enough of the ethylene diamine in to replace 4 of the waters, and we make this complex here. So this has 2 ethylene diamines and still 2 waters on it. Again, this is another way that we'd write it, and maybe like this. So here are the 4 things that I've made so far. Okay, and now we can stop and make a prediction. If I added a little bit of ethylene diamine, I got 1 on there. If I add a little more, I get 2 on there. So what do you hypothesize would happen if I added a lot of ethylene diamine? 1, 2, 3. Thank you. Yes, 3. Okay, so we'll see. We'll see if that happens. Okay, so with this beaker then, I'm going to add a bunch of it. Maybe I should do this from the back. Is this better? No, this is better. Okay. So now, let's add a little more, just for good measure. There we go. Okay. So now it made yet a different color. This one's purple, right? So this one, so here we add even more ethylene diamine. We get this thing that's dark purple. And now it's got 3. So every water is replaced by an ethylene diamine. And we might draw it like this and abbreviate it like that. So now here are all 5 of the things I've made so far. But I have 1 more beaker. And so with this one, last beaker, I want to add, get a different molecule, which is in here. Okay. With my last beaker, I'm going to add this compound, which is called dimethylglyoxime. It's a little bit bigger than the other ones we've seen, but again, this is a carbon here and a carbon, and it's got these 2 nitrogens, which looks kind of similar to the ethylene diamine. And when we add this one to the mixture, ready? Got an extra stir bar in there. it turned red, right? It turned red and it made a solid. So I'll leave after you're done, you can come up and check this out. Sorry, I'll stop the ringing noise. So what you've just seen there is the following reaction. So there's the dark red, and the molecule that we've made is this one. So it's got just 2 of these dimethylglyoxenes around the nickel, and it looks a little bit different. It's only got 4 things bound to it, and it makes this red solid. So here's a cartoon of what happens, and then here's the full range of every compound that we've made. Okay, so in every case, they're nickel 2, all the same, except they've got different stuff bound to them, and that makes them all different colors. Yes, question? The overall complex doesn't, because each of the ligands has a -1 charge. That's advanced. Yes? That's right. That's right. So this oxygen, this is sort of advanced too. The hydrogen's kind of shared between these 2 oxygens in this complex, but it makes this solid red. Okay, so what the heck, right? Why are we looking at all these nickel complexes other than the fact that I think it's really cool and it makes nice colors? Okay, here's the periodic table I showed you before, and here it shows you which metals are important in biology, and I promised you a story about a medicine. And I'm talking about nickel, which is not gray. So the ones that are used in medicines are supposed to be gray, and this one's not. So what's the deal? Well, the reason I'm talking about nickel is that nickel's in the same family with platinum, and I do want to talk about platinum. That's the story of the day. And the reason that the periodic table exists the way it does is because of these relationships among elements in a family. So one column we sometimes call a family on the periodic table, and it's entirely... It's really hard with the lab coat. Okay. The reason that we call these vertical relationships families is because they have properties in common, and it's a lot like your family, maybe. So, you could sort of imagine that platinum's like the big brother of nickel, right? And if you imagine that this row is like your class at school with all kids about the same size-ish, and then this would be some higher grade, and that would be some higher grade. If you had some big brother in another grade, you might have a lot of stuff in common, right? You might look alike, you might like the same movies, you might both play soccer. But also there's some chemistry and there's some differences in people that's different. So I have a little sister. She always hated the fact that all the science teachers thought that she would like science because she didn't very much like science. So just as with elements, you have to be a little bit cautious. You can't assume that the little brother is going to be just like the big brother or sister. But often, there are a lot of properties they have in common, right? And frankly, I couldn't afford to do this demonstration with platinum. Platinum's really expensive. And also, and I wanted to have, tattoo money left over. So, and also, frankly, nickel makes better colors. So that's why we're doing it with nickel. But the complex we're going to talk about is the big brother of nickel, which is platinum. And as you'll see, the platinum complex is going to look a lot like this nickel complex here. So just hold that thought, for a minute. Okay, so that's why. So again, this some of the chemistry of this work was covered by Dr. Iona Black, who gave a talk 2 weeks ago. I had already promised to talk about medical metals, and frankly, this is the best story in bioinorganic chemistry, and I could not let go of it. I had to tell it anyway. So you saw some of the chemistry from her, but I'm going to tell you some other parts of the story just because, frankly, I can't resist doing it. So this gentleman here, Barnett Rosenberg, had a really good idea in 1965, which starts the story. He thought about magnetic field lines that were around a magnet. So this is an experiment in physics, right? If you take a bar magnet, like one of my stir bars, and you shake iron filings around it, they orient themselves to define field lines, right? Maybe you've seen that in physics. And those field lines kind of reminded him in some way of the spindles that form during cell division. So we have an insight from physics and an insight from biology that came together in his head. And he thought, these field lines look kind of like these spindles. And so he wondered if maybe cell division might be some kind of electromagnetic phenomenon. Now, I need to tell you that he was wrong about that, right? But it doesn't matter. The story has a happy ending, as you'll see. But my point is that great ideas don't always have to start out on the right track. So Barnett Rosenberg had this good but wrong idea. The experiment that he did was he grew E. coli bacteria, recently in the news for invading spinach and making people sick. But we use them in the lab a lot. They're not always dangerous. He grew them in a petri dish in the presence of platinum electrodes, and he put like a field across the electrodes. And what he saw was this really weird behavior in the cells. So here are E. coli cells that look normal. And when he grew them in this dish with his electrodes and hooked up to a power supply, the cells did really weird stuff. They got bigger and bigger and bigger, but they never divided. So that was weird, right? But luckily, Rosenberg was a really careful scientist, and so he did the control experiment, and he turned the power off, and the same thing happened. So imagine, if your television at work, if your television at home worked without the plug in, you might think something strange was happening. And so clearly, this effect he was seeing was not anything to do with the power. Probably made the electrodes react faster, but he could plug it in for a while, take it off, and the effect persisted. So clearly, there was something interesting, different going on. And luckily, he had the persistence to not just throw the thing in the trash and go home. He diligently figured out what was happening. And it turned out, the punchline of the very long story is that this molecule, cisplatin, was the chemical agent causing the change. And so I made this sort of homemade cisplatin for you. There also aren't metals in the molecular model kits. More tyranny. But I made some. And I also had to, make my usual homemade nitrogens. So here's cisplatin. Oh, it's actually in the other orientation, isn't it? On this. And it's a very reactive molecule. So this thing had actually been made more than 100 years before. So when I was showing you all that nickel stuff, those are all complexes that are just for fun, just for show, at least today, right? And 100 years ago, people had made complexes just like this, just to make them. Not with any medicinal application in mind, just for the basic research. These had already been made in 1845. In 1893, Alfred Werner figured out what the structure was. And it turned out this thing was medicinally active against these cells. So that's all very cute, Making really big E. coli is like a good party trick, right? But ultimately, that's not so applicable, right? And so the thing that made this really exciting is that cisplatin cured tumors in mammals. And so I'm going to show you one disgusting mouse picture, but it has a happy ending for the mouse, okay? So this is a picture from Rosenberg's original 1969 paper. And you can see this poor mouse has got a tumor here under his armpit. See, it's a big lump. And when this mouse was injected with this compound cisplatin, the tumor over many days got smaller and smaller and smaller, and the mouse also got fatter and fatter and fatter, you can see. But by day 36, the mouse was cured. And so this and lots of other experiments like it really showed that this funny thing that happened in bacteria had profound and really useful effects in humans. And so what happened after that happened pretty fast. That was a 1969 picture that I showed you. In 1971, cisplatin, the compound, entered clinical trials in humans, and it was approved in 1978. Any of you who know about drug discovery know that's blindingly fast. It was really very successful. And this compound is licensed by Bristol Myers Squibb just up the road in Wallingford. And more recently, they launched a second-generation medicine, which is this molecule, carboplatin, which is one that's used today. Now, this isn't a perfect drug. It's not active against all kinds of tumors. That's one big problem. It causes bad side effects, like a lot of kinds of chemotherapy. People lose their hair, they get very sick. And some tumors tend to come back resistant to the drug. So sometimes you can beat the cancer one time, but then if you don't get it all, when it comes back, somehow the cells can resist the medicine. And so there's a lot of work still to do about this drug, but it's really been incredibly successful for many, many people. And I want to show you one person you may know who was cured by this drug. So does anybody know who? Yeah, Lance Armstrong. So I realize, you guys are way cooler than I am. This is probably totally passé, right? This is like so last year with the rubber bracelets, right? but, but at least, a year ago, these rubber bracelets were meant to support Lance Armstrong, who's this gentleman. And he's a spokesperson for Bristol Myers Squibb and was cured partly by these platinum drugs, as have been many people. And so this is now, I think, about the third best-selling anti-cancer medicine, and mostly used. And again, while not perfect, it's really cured a large number of people. And so it was an accident. It was an accident, but it's been really, really a successful medicine. Yes?
How did you decide to inject it into a mouse? How to go from E. coli
Well,
to mouse?
there's a joke that cancer's been cured in E. coli many times. So, you can do things happen in E. coli, but of course you always wonder about the human applications. And something that affects cell division so much, you'd think about what it might do to a cell that's dividing all the time, which is what a cancer cell does. It would more specifically damage those than one that wasn't dividing all the time. Anybody else? Okay, so the way that, just real quickly, because I'm going a little over, the way we think cisplatin works is that it goes in and binds to DNA, and it kinks the DNA the way I've shown. So what actually happens is that the chlorides, these two chlorides come off. So, all right, chlorides come off, and it binds to a piece of DNA. So if I'm DNA, the cisplatin binds to me, and when it does that, it makes it sort of kink and twist, and that causes a lot of problems with the copying of DNA, and with the reading of DNA, and with the repair. And again, as the question addressed, because tumor cells are dividing more often than normal cells, it's relatively more damaging to a cancer cell than to a healthy cell. So that's the way it works. But there's an awful lot of other biology and chemistry behind that rather glib description. So the summary then of my second part is that platinum compounds like cisplatin were accidentally discovered to be very effective medicines against cancer, but again, they're not perfect, and there's still a lot of work that needs to be done about them. So if you'll just give me like a minute at the end, I just want to say a few things about chemistry, because you've seen a couple different kinds of science today, and I think while I admire all fields of science, I think there's amazing biology, and as Rosenberg showed, there's really great stuff that happens when you're aware of both biology and physics, right? At the end of the day, I'm a chemist, and so I think it's a fair question what I think is the good thing about chemistry. So there are two things. The first thing that I think is really cool about chemistry is that we get to make stuff. And so in a lot of kinds of science, including some kinds of chemistry, we try to figure out what's true about nature, what's true about the world. But chemistry, more than some other kinds of science, gets to invent our own new stuff, make new materials and make new molecules that have never been made before. And that is a buzz for a lot of us. That's pretty cool. And so when I say creative, I don't mean like creativity and experiment design, I mean actually making stuff. And that's what attracts a lot of chemists to chemistry. And finally, for me, quite frankly, there's this thing that I like to call the Goldilocks effect, which is that I really liked science a lot, but for me, biology is too big. Biology is very complicated. There are lots of big molecules, they're doing a lot of stuff, and for me, that was big. Physics is either too small or too big, depending on, if like atomic physics is really tiny and then astrophysics is really big. So, like Goldilocks, right? Too hot, too cold, just right. For me, science was too big, too small, just right. So I think there's certainly a room for lots of kinds of science. I certainly would never say anything bad about my colleagues in science. But for me, these two things, the ability to make new stuff and the Goldilocks issue, were the two things that made me a chemist. And so finally last, I just want to show, in Nature last month, this gentleman, Philip Ball, went around and surveyed a lot of really leading chemists and asked them what the most important questions in chemistry are right now. And so I offer these as sort of a to-do list for your generation. Right, here are the most important things that really smart chemists think are important things to know. So first of all, how do we design molecules with specific functions and dynamics? How do we make the next cisplatin be found on purpose and not by accident? Right? How do we plan things? Secondly, what's the chemical basis of the cell? What does chemistry have to say about biology? How do we make materials that we need for the future in energy, aerospace, and medicine? Can we make a chemical that gives us a better fuel cell? Can we solve some energy problems? Can we store hydrogen? All of those things we don't know how to do yet. What is the chemical basis of thought and memory? So, that is sort of the last, I told you at the beginning there was nothing mystical about organic chemistry, but there's something a little mystical about thought, isn't there? And so understanding, what chemistry has to say about how memories are stored is a pretty profound question. Speaking of profound questions, how did life on Earth begin? You don't get much more profound than that. How could we look for it if it happens on other planets? What should we look for? What conditions are necessary? And finally, how can we explore all the possible permutations of all the elements? We make stuff, but we can't make everything. There's no way that we could make every combination of molecules, of atoms in a molecule that you could imagine. And so, how should we address this problem? How should we even try? Or should we even try? These questions are some of the most profound that are left to do for, as I said, for your generation. I mean, I'm not so old. I'll have a crack at it, but you guys have more time than I do. Okay, so I just want to do two other items of business. One is a nice student asked me to put up this slide advertising SciQuest 2006. If you are hooked on science and you want to see some more, the nice kids who do the Yale demos group are having a thing on Saturday, November 4th at Dwight Hall. There's an email down here at SciQuest2006 at Yahoo, and I believe they're going to have handouts for you when you go. So you can get your, I think I've probably had more fun than anyone today because I got to mix stuff, right? So you could do that too. And I also want to really thank Professor Anissa Ramirez. This is the last Science Saturdays talk for the year, and Anissa does a wonderful job organizing and promoting this, so I'd like to have everyone applaud. Thank you. Yeah.